Algorithm improvements in ChatGPT. The takeaway from this is that size alone does not account for improvements in the models. They are now realizing that increasing size is providing diminishing returns. In the future, smaller models with cleaner data will play an increasing role in the world of AI. Over successive GPT versions, OpenAI and other similar organizations have worked on improvements along several axes. 1. Model scale/capacity. Later models generally have more parameters, more layers, or otherwise more capacity to represent complex functions. That said, purely scaling up is not sufficient. Efficiency, regularization, and training methods also evolve. 2. Training data, diversity, and curation. Newer models typically use more data, more up-to-date data, more varied modalities, text, images, etc., and better filtering or pre-processing to reduce noise, bias, or undesirable content. 3. Multimodality. Early GPTs handled only text. Later ones began to ingest or reason about images, audio, and other modalities or combine modalities. For example, GPT-4 is described as a multimodal model, accepting images plus text, though its output is text. 4. Context window/memory. The length of context, how many tokens of previous text the model can take into account, has grown. This allows the model to handle longer documents, more sustained conversation history, or tasks over large texts. Some newer versions push these limits further. GPT-4 variants are described as having much larger context windows than earlier GPT-3/GPT 3.5 models. 5. Better reasoning, factuality, and hallucination control. A known weakness of early large language models is hallucination, producing plausible-sounding but incorrect or nonsensical statements. Later versions aim to reduce that, improve grounding, increase consistency, and handle reasoning or logic more robustly. For instance, GPT-4 is claimed to reduce hallucinations relative to GPT 3.5 in various internal factuality evaluations. Also, OpenAI reports that GPT-4 makes progress on benchmarks, like truthful QA, that test how models avoid mimicking false statements. 6. Instruction following, alignment, and safety. As the models are exposed to human users, there's more emphasis on guiding their behavior, so they do what the user intends, not just what the probability model would normally produce. This includes reinforcement learning from human feedback, RLHF, alignment techniques, fine-tuning to avoid harmful outputs, and safer behavior. GPT-4's report mentions using model-assisted safety pipeline, additional safety training prompts, and rule-based reward models to steer behavior. Also, newer versions are better at refusing or safely handling disallowed inputs. 7. Task specialization and modularity. Over time, there is more ability to specialize or fine-tune the models for certain tasks, e.g., coding, mathematical reasoning, agents. For example, GPT-5 has a codex variant optimized for coding tasks. Also, newer versions tend to be better at agentic behavior, i.e., executing multi-step tasks, planning, invoking tools, rather than just passive text generation. According to OpenAI, GPT-5 is better at autonomous task completion, agentic capabilities. 8. Efficiency, latency, and cost. It's not enough to make models more powerful. They must also be practical to run. So improvements in inference speed, memory efficiency, quantization, model pruning, distillation, and hardware utilization are important. OpenAI often highlights changes that reduce cost or latency while maintaining quality. For instance, the GPT 4.1/4.1 mini/nano models are introduced with claims of improved efficiency and lower cost. Also, Newer versions sometimes allow longer but cheaper context windows. 9. Better generalization and robustness. Later models tend to be more robust to adversarial inputs, out-of-distribution prompts, style shifts, or domain changes. They generalize better across many tasks without needing heavy fine-tuning. 10. Ecosystem and tooling, e.g., tools, memory, plugins. Over time, OpenAI and its systems embed more infrastructure, e.g., tool use, APIs, plugins, access to external data, memory systems for conversations, better integration with user files and uploads, and improved prompt engineering frameworks. For example, newer models are better at working with uploaded files, documents, and providing deeper insights. GPT-4o updates include improvements in how the model handles multimodal uploads and more natural writing. Some specific version-to-version highlights: GPT, GPT-2. Significant increase in scale. GPT-2 had 1.5 billion parameters versus GPT's smaller size, and improved text generation coherence and length. GPT-2, GPT-3. Huge scale jump from approximately 1.5 billion to 175 billion parameters, better zero and few-shot performance. GPT-3, GPT 3.5/Instruct GPT/CHAT GPT. More alignment and instruction following via fine-tuning, improvements in safety and user alignment. Instruct GPT is an early attempt to make the model more controllable via human feedback. GPT 3.5 to GPT-4. Among the improvements cited, better reasoning, logic, and common sense capabilities, multimodal inputs, text plus images, support, substantial improvements on benchmarks, e.g. MMLU, and on internal evaluations of factuality and hallucination reduction. More robust safety and alignment, better refusal behavior, less toxic outputs. GPT-4. Variants /GPT 4.1/GPT-4o/GPT 4.5. These are refinements rather than wholly new architectures. Improvements include better instruction following and more intuitive responses, longer context windows, e.g., 128K tokens and possibly beyond, in newer variants, efficiency, speed, and cost trade-offs, smaller variants that still retain high capability. Reduced hallucinations in GPT 4.5, less confident wrong answers. GPT-4/prior arrow GPT-5. The announced improvements include stronger coding performance, especially in front-end generation, repository-level reasoning, aesthetic design, bug catching, etc. Better agentic/autonomous task execution capabilities, improved reliability, lower tendency to confidently produce wrong answers, less prone to confidently wrong. New codex variant for coding optimization, GPT-5 codex, for software engineering tasks. Better deployment outcomes, improved accuracy, reliability, quality, and speed in real-world workflows, as per early rollout reports. As an example, OpenAI's release of GPT 4.1 and its mini nano variants highlight improved instruction following, coding, and a larger context window. Another recent claim, GPT 4.1 models support up to 1 million tokens of context, a dramatic jump over earlier context limits. Algorithmic/architectural changes beyond just size. While OpenAI does not always publicly disclose all internal architecture or algorithmic innovations, here are some kinds of improvements likely involved, or partially disclosed, over time. Better training objectives/loss functions. They may refine the loss functions or regularization techniques used, or combine multiple auxiliary losses, e.g., for alignment, safety, calibration. Advanced optimization/learning rate schedules/regularization. More sophisticated curricula, adaptive learning rates, gradient techniques, weight decay, etc., as models get bigger and more complex. Curriculum learning and data scheduling. Ordering or weighting of training data matters a lot. Later models might use better curriculum strategies to present easier-to-hard examples or more balanced data. Mixing of high-quality, human-labeled data for alignment with large-scale, unsupervised data. Techniques like RLHF, reinforcement learning from human feedback, supervised fine-tuning with human labels, preference modeling, etc. Model architectures/modifications. Though the high-level backbone is still transformer-based, there may be tweaks to attention mechanisms, memory modules, efficient sparse attention, or architectural innovations to support longer context or multimodal inputs. Modularization and internal routing. In large models, gating, sparsity, or mixture of experts architectures can help allocate capacity dynamically, depending on the input. Better calibration, probability estimation, and uncertainty modeling. To reduce overconfidence in wrong answers, later models may be better at estimating uncertainty or declining to answer. Post hoc correction/reflection/self-consistency. Some methods incorporate internal reflection or chain of thought style checks or multiple passes to reduce errors. Quantization, pruning, distillation, and efficient deployment techniques. To make inference cheaper/smaller, they may distill or compress large models into smaller ones, or use lower precision arithmetic with minimal loss of fidelity. Tool integration/retrieval and external memory. To ground outputs in external, up-to-date knowledge or to use external tools, APIs, plugins, search. Later models often integrate retrieval or tool calling mechanisms. Safety and alignment pipelines. As models become more widely used, OpenAI invests in safety curation, adversarial testing, filtering, behavior shaping, rule-based models, etc., caveats, and open questions. Because OpenAI does not fully reveal all internal design details, some of the above is inferred or based on what they do disclose. The secret sauce evolution is not always public. Bigger models are not automatically better. Gains often require smarter training strategies, architectures, and alignment work. The scaling law is helpful, but has diminishing returns. While OpenAI claims many improvements in benchmarks and behavior, real-world performance, in user deployments, also depends on prompt engineering, system design, memory, tool support, and so on. Sometimes newer versions trade off latency or computational cost for improved accuracy. Model variants may aim to balance those trade-offs. The more advanced a model is, the more important its safety and alignment pipeline becomes. Complexity and risk increases too.